2 electrons from the s orbital and 1 electron from the d orbital will go. So what will be the electronic configuration in 3 plus oxidation state? It will be 3d1. So if there are d electrons, what happens with the absorption of light? It will move to the electrons. The d electrons will move to the higher energy level. Because of the dd transition, colors will be shown. The final stability constant is a product of the stability constant of each step. Okay, so this is very important. If the K1, K2, K3 are the stepwise stability constant for each step. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with the last session of the chapter Coordination Compounds. So in the last session, we discussed about the limitations of valence bond theory, and then we moved on with the next and last theory, that was crystal field theory, right? Yes, and then we studied what a spectrochemical series as well as how the electrons are filled in the various d orbitals according to whether it is an octahedral complex or a tetrahedral complex, right? So all this we are being discussed in the last session. So in today's session, we are going to study about the color in coordination compounds. So in the last session also I discussed about color, right? Coordination compounds will show colors. Now why it is that we are going to study now, right? And the influence of ligand on the color, limitations of crystal field theory, bonding in metal carbonyls, stability of coordination compounds, and the various application of coordination compounds. By that we'll come to an end to this chapter. Okay, so beginning with the color in coordination compounds. So why does this coordination compounds shows colors? Okay, so let's see. When white light is passed through a solution of transition metal complex, the solution absorbs certain electromagnetic radiations of white light. So through a coordination compound, till now we have studied about coordination compound, right? So through a coordination compound, if you are passing white light, what happens is certain parts of this electromagnetic radiations will be absorbed by the coordination compound. The color of the complex is complementary to which it is absorbed. So which color is absorbed? A particular range will be absorbed, right? A particular wavelength. According to that wavelength, there will be an appropriate color also, right? So that color will be absorbed. The complementary color will be shown by the compound. Okay. So for example, if a coordination compound is showing a color blue, okay, if the coordination compound is having a color blue, that means it has absorbed a color which is complementary to that is orange color. So a white light is passed. If the orange color is absorbed by the coordination compound, the color of the coordination compound will be blue. It will be complementary to each other. If it is absorbed color is red, the color shown by the compound will be green. If the absorbed color is green, then the color shown by it will be red. So this is how the complementary thing works. Okay. So whichever color is absorbed, the complementary color will be the color which is shown by the coordination compound. Clear? Right. Now, example, the complex titanium H2O6 3 plus, which is violet in color. It is a violet color complex. So this is an octahedral complex. Of course, it is an octahedral complex. Why? Coordination number is 6. Aqua is monodentate. So of course, the ligand number, the number of ligands and the coordination number will be equal, right? So where the single electron Ti3 plus is a 3D1 system in the metal d orbital is in the T2G level in the ground state of the complex. So what does that mean? Titanium. So what is the oxidation number of titanium here? Aqua, it is neutral. So of course the charge or the oxidation number of titanium will be 3 plus, right? So titanium, the electronic configuration will be argon 3d2 4s2. Right. So in this particular complex, when titanium is forming a complex with aqua TiH2O6 3 plus, what is the oxidation state or oxidation number? It is 3 plus. So what is the oxidation state here? Titanium 3 plus. So what happens? 2 electrons from the s orbital and 1 electron from the d orbital will go. So what will be the electronic configuration in 3 plus oxidation state? It will be 3d1. Okay. So only 1 electron is present in the d orbital. Okay. So as it is an octahedral complex, in last session we have studied how the crystal field splitting takes place, right? Okay. So all the 5d orbitals will be present in the ground state, okay, which is having the same energy. Then what happens? When the ligand approaches, the d orbitals will split into 2, right? So in an octahedral complex, how does it split? Into 2 and 3. That is Eg on the top and T2G on the bottom. T2G on the bottom, right? So now, as said, in titanium 3 plus only one electron is present. So of course, where will that electron be present? That will be present in the T2G orbital, right? So I hope it is clear, right? Now the next higher state available for the electron is empty Eg level. So these 3 T2G are having that is these 3 orbitals are having the same energy, right? All the 3 T2G. Now which is the higher energy level here? That is Eg. So the next higher energy level which is present Eg, which is free, right? Okay. So if light corresponding to the energy of yellow-green region is absorbed by the complex, it would excite the electron from T2G level to the Eg level. Okay, that means, so when the coordination compound of titanium absorbs the corresponding yellow-green region light, what happens? The T2G electron, the electron which is present in this energy level will move to the higher energy level, right? That is from T2G1, it will go to EG1. That means from T2G only one electron was there. This electron will jump to the higher energy level. So the electron will jump from the T2G energy level to the higher EG level when the corresponding light is being absorbed, right? So the crystal field theory attributes the color of the coordination compound to DD transition of the electron. So why does this color is shown, or why the coordination compounds are generally colored, is because the DD transition. So this is very important, because of DD transition. That means from one d orbital, all these are d orbitals only, right? So from the lower d orbital, what happens when it absorbs the light? Okay, what happens? It will get energy, right? It is absorbing electromagnetic radiations, means it will get energy, it will move to a higher energy level. So because of a transition within the d orbital, from one d orbital to another d orbital, it is jumping. So that is why it is called as DD transition. So because of this DD transition, the color is shown by the coordination compound. So based on which color it is absorbed, the corresponding or the complementary color will be shown by the coordination compound. So I hope it is clear. So this point is very, very important. Because of the DD transition, the color is shown by coordination compounds, right? Now the influence of ligands on the color. So are the ligands also important there? Okay, so the oxidation state of the coordination compound is necessary. The number of d electrons, if it changes, the color changes. That and all is okay. But is there an important for the ligands? Let's see. The absence of ligand, crystal field splitting does not occur, and hence the substance will be colorless. So ligands are of course important here. If there is no ligands, of course there will be no crystal field splitting itself which is taking place. Because of the presence of the ligands, either it is strong or weak, the splitting will take place, right? So in the ground state, what happens? The metal will remain as it is. When the ligand is approaching, the splitting is taking place, right? So ligand plays an important role here. If the ligand, the number of ligands, and if the ligands is absent, what happens? Of course the crystal field splitting would not take place, and hence the compound will have no color also, right? So for example, removal of water from TiH2O6Cl3 on heating renders it colorless. So this is a colored compound. This is a coordination compound, right? But what happens if we start heating it? What happens? This aqua part, H2O, will be lost, right? Once we are heating it. So if the ligand is lost or removed, what happens? It will become colorless, right? Similarly, anhydrous copper sulfate is white. So the copper sulfate crystal you generally see is blue in color, right? Now why is this blue in color? Because of the presence of this 5H2O. Okay, CuSO4 5H2O. So this is very important. Because of the presence of this water only, it is blue in color. So if this water is being removed, that is if it is anhydrous, the color of copper sulfate would be white. Okay, so the copper sulfate that you are seeing is with the water itself, right? Now NiH2O6 plus complex, which forms when nickel 2 chloride is dissolved in water. So this is actually a green color complex. Nickel H2O6 plus, it is a green colored complex, coordination compound. If the didentate ligand ethane 1,2-diamine, we are familiar with this ligand, right? Yes, ethane 1,2-diamine is progressively added in the molar ratios 1:1, 2:1, 3:1, the following series of reactions and their associated color changes occur. So what we are going to see here now is when we are adding a ligand to it, what happens to the color of the coordination compound, to say that the importance of ligand. Okay, so initially the color of nickel H2O6 2 plus is green in color. Okay, so this is green in color. So now what we are going to do, we are going to add ethane 1,2-diamine in the ratio 1:1, 2:1 and 3:1. So here the coordination compound remains the same, but we are adding on some extra ligands here. So let us see, initially the color would be green, right, to which we are adding ethane 1,2-diamine. So now what happens, a new coordination compound is formed which is having pale blue color. We have added another ligand. So what happens, the number of water molecules has changed, right? Okay, the number of water ligands has changed, aqua ligands has changed, because ethane 1,2-diamine has included in the coordination compound now. Okay, so the color has changed. Now to that particular coordination compound which is pale blue in color, again we are adding ethane 1,2-diamine. Now what happens, we get a new coordination compound. Again the number of aqua ligands has changed, right? It was H2O4, here it is H2O2 here, and 2 ethane 1,2-diamine is being present. So now the color is blue or purple, right? Now again to this blue purple coordination compound we are again adding ethane 1,2-diamine. So now finally you will get nickel En thrice. Okay, so this stands for 3 ligands of ethane 1,2-diamine which is violet in color. So I hope it is clear. Initially it was green, to which we added 1 ethane 1,2-diamine, another didentate ligand. It became pale blue in color. Then you got a darker blue, and then finally a violet color. So I hope it is clear, the importance of ligands. Clear? Right. Now the limitations of crystal field theory. Even crystal field theory had its own limitations. So let's see. The crystal field model is successful in explaining the formation, structure, color and magnetic properties of coordination compounds to a large extent. We discussed about magnetic property, discussed about color as well. Because of the DD transition, colors are shown by the coordination compounds. Even that we have discussed. Then in where the d orbitals, or which d orbitals the electrons will be present. If it is T2G, EG, based on octahedral complex, tetrahedral complex, all those were being discussed, right? But the crystal field theory assumes that the ligands are point charges. It follows that anionic ligands should exert the greatest splitting effect, but anionic ligands are found at the low end of the spectrochemical series. So according to the crystal field theory, in the beginning itself, we have discussed that the ligands are considered as point charges if they are anionic. Okay, and anionic ligands are the ones which are supposed to show high crystal field splitting. But according to the spectrochemical series we have studied, okay, that is the decreasing or increasing order of the strength of the ligands. The anionic ligands, that is your halogens, all of that comes towards the end of the spectrochemical series. That is, those are generally weak ligands. Okay, so that was an assumption which was wrong, right? Now it does not take into account the covalent character of bonding between ligand and the central atom. So in here, as it is considered as point charge, this was also discussed that according to crystal field theory, the metal and the ligand bond is considered as ionic. But there was no discussion based on the covalent character of the metal ligand bond, right? And it could not explain the color of substances with fully or empty d orbitals. Okay, so if there are d electrons, what happens with the absorption of light? It will move to the electrons. The d electrons will move to the higher energy level. Because of the dd transition, colors will be shown. But if it is completely filled, or else if it is completely empty, will it show any colors? It will show, but how does that happen? The explanation for it was not given by the crystal field theory. So I hope it is clear. Now moving on to the bonding in metal carbonyls. Now what are metal carbonyls? Let's see. The homoleptic carbonyls, that is compounds containing carbonyl ligands, which is carbonyl ligand CO, right, are formed by the most of the transition metals. Okay, so metal carbonyls means it is a coordination compound of a metal and the ligand there is always carbonyl, that is CO, right? Okay, so NiCO4 is tetrahedral, FeCO5 is trigonal bipyramidal, CrCO6 is octahedral, MnCO10 is made up of 2 square pyramidal, CO2CO8 has a cobalt-cobalt bond bridged by the 2 carbonyl groups. So let's see here. First one is tetrahedral. It is a metal carbonyl of nickel. Right, the metal which is present here is nickel. As you can see here, nickel and 4 CO ligands are there. That is carbonyl ligands. The shape is or the geometry is tetrahedral here. Now, trigonal bipyramidal in case of FeCO5. Okay, that is pentacarbonyl. So that is FeCO5. So as you can see here, iron is in the center and there are 5 carbonyl ligands. So the next one is octahedral, that is CrCO6. Here also in the center there is a central metal atom which is chromium. Surrounding it you have 6 carbonyl ligands. So in all these cases you can see the ligands is always carbonyl. So that is why it is called as a metal carbonyl, right? Now in the case of Mn2CO10, you can see here it is made up of 2 square pyramidal structures. So here one square pyramidal will be there, here another square pyramidal, and these two are joined, and there is an extra bond between the manganese and manganese. Okay, now the last one you can see here is CO2 CO8. Okay, so there is a cobalt bond bridged by 2 CO groups. Okay, so you can see here this is one cobalt atom, another cobalt atom. Surrounding to this cobalt atom there are 1, 2, 3 and 4 carbonyl ligands, and to this cobalt atom 1, 2, 3, 4 ligands are present. Okay, and there will be a bridge between these 2 cobalt atoms. So I hope it is clear. So these are metal carbonyls. Now what is the bonding in these metal carbonyls? So the metal carbon bonds in metal carbonyls have both sigma and pi characters. So the metal carbonyl bonds are generally very strong. Now why this is? Because there is sigma as well as pi bonds which is present. So how is this happening? Let us see here. A sigma bond is formed when the carbonyl carbon donates a lone pair of electrons to the vacant orbital of the metal. So generally we have studied the ligand will be having the lone pair or extra electrons which it will donate to the metal, right? So how is the sigma bond formed? When the carbonyl carbon, so you can see here C triple bond O, which is carbonyl ligand, right? So the carbonyl carbon, it will have these electrons which it will donate to the vacant orbital of the metal. So this is how a single bond, that is a sigma bond, is formed. Clear? Now a pi bond is formed by the donation of a pair of electrons from the filled metal d orbital to the vacant anti-bonding, that is pi star orbital of the ligand. Okay, that means now at the same time when the carbonyl carbon is donating electrons to the metal, which is generally supposed to happen in a coordination compound, the same time the orbitals of the metal, right, the filled orbitals of the metal, from there the electrons will be donated back to the carbonyl ligand. Okay, so as you can see here, it will be donated to the vacant d orbital of the carbonyl carbon. So in both ways it is happening. So here a pi bond will be formed and here a sigma bond will be formed. Okay, so that is how this synergic effect is formed due to the metal to ligand bonding, and this synergic effect strengthens the bond between the CO, carbonyl, and the metal. That is why this bond will be very strong, because there will be sigma and pi. And another one important point to remember is, generally as I told you, in a coordination compound, the ligand will donate the electrons to the metal. But in metal carbonyls, as the ligands is donating the electrons to metal, as well as the metal is donating electrons to the ligand. So that is called as back bonding of the carbonyl compound. So that is very important. It is called as back bonding. That is, the metal is donating the electrons to the carbonyl carbon. So in both way, the bonding is taking place in one direction as well as the another direction. So it totally forms a very, very strong bond. So I hope how sigma and pi bond is formed is clear for you. Right. Now, the stability of coordination compounds. Now moving on to the stability of coordination compounds. The stability of a complex in a solution refers to the degree of association between two species involved in the state of equilibrium. So to how much extent it is getting associated, based on that we can say whether the coordination compound is stable or not. The stability can be expressed quantitatively in terms of stability constant or formation constant. So for example, you have a metal here which is represented as M, and there are 4 ligands L. So it forms a coordination compound ML4. Okay, ML4 it forms. The stability constant beta, okay, the symbol used is beta, is written as the molar concentration of the coordination compound divided by the molar concentration of the metal and molar concentration of the ligand raised to the power which is equal to their coefficient. So how many are there? 4 ligands are there. So it is raised by 4. Okay. So this we have already studied this format in equilibrium constant, right? So for this reaction, greater the value of stability constant, greater is the proportion of Ml4 in the solution. Okay. So if the concentration of, see, as you can see here, this is directly proportional to, that is the stability constant will be directly proportional to the concentration of the coordination compound, right? So if more coordination compound is present, that means the coordination compound is of course stable, right? That is the stability constant will be more. Stability constant is more means what you can predict from there? Yes, the coordination compound is more stable, right? So free metal ions exist in the solution so that metal will usually be surrounded by solvent molecules which will compete with the ligand molecules L and will be successfully replaced by them as follows. So what we are going to do? We are going to successively add ligands here. So in the first step, you can see there is a metal to which a ligand is added. So what happens? A coordination compound formed is Ml. Okay. Then the stability constant K1 will be Ml by M into L. So as you can see here, what is in the product? It is Ml, right? And what are the reactants present? M and N. So this is the stability constant for the first reaction. Now to this coordination compound, we are going to add one more ligand, Ml. To Ml, another ligand. So it becomes Ml2. So what will be the stability constant? It is Ml2 divided by Ml into L. Right. Now the reactant is Ml here. Right. Now in the third one, Ml2. To this Ml2, another ligand is being added. You get Ml3. So the stability constant will be Ml3 divided by Ml2 into L. Okay. Now to Ml3, again one more ligand is added. Ml4 is obtained. So the stability constant, this is the final stability constant that you can see here. Okay. So this particular reaction we have seen here, this is actually a successive steps which is happening. Okay. So the altogether reaction is what is written here. That is metal plus 4 ligands will give you Ml4. So the successive steps is being written here. So where K1, K2, K3 and K4 are referred to as the stepwise stability constant. For each step the stability constant is mentioned. So alternatively we can write it as M plus 4L gives Ml4. That is what I just said now. So the stability constant of together it is written as Ml4 divided by M into L raised to 4. So this 4 stands for the stoichiometric coefficient here, right? So the stepwise and overall stability constants are therefore related. So this relation is important. The final stability constant is a product of the stability constant of each step. Okay. So this is very important. If the K1, K2, K3 are the stepwise stability constant for each step, then the total or overall stability constant will be a product of these. Okay, will be a product of these. Okay, and if there are n steps involved, it will be K1 into K2 into K3 etc. multiplied by Kn. Okay, so the reciprocal of the formation constant is called instability constant or dissociation constant. So this was in the case of association, right? Each ligands are being formed. So it is called the stability constant. What will be the inverse of it? It will be instability constant or dissociation constant. So I hope it is clear. Now to moving on to the last part, what are the applications of coordination compounds? Okay. So in many qualitative and quantitative chemical analysis, that is color reactions are given by metal ions with a number of ligands which help in detection and estimation. So they are easily to detect and estimate because of course they are colored coordination compounds, right? Now the hardness of water can be estimated by simple titration with EDTA which forms stable complexes with calcium and magnesium. Ca2 plus and Mg2 plus are generally the one which causes hardness of the water. Calcium and magnesium ion causes hardness in water. So how we can estimate the hardness of water? Using EDTA, that is a coordination compound with sodium it is forming. Okay, clear? Now articles can be electroplated with silver and gold much more smoothly and evenly from solution of the complexes AgCN2 minus and AuCN2 minus that form a solution of simple metal ions. Okay, so electroplating, we have already studied this in electrochemistry chapter, where using metal rods, we are going to electroplate into substances we require. So if you have to electroplate silver or gold, there are other methods which you can use, but it is preferred to use coordination compounds like this because it is preferable, right? Now some important extraction process of metals such as gold and silver make use of complex formation. Now the coordination compounds are used as catalyst also. This is also very important. They play a very important role as catalyst. For example, Wilkinson catalyst, which is PH3P thrice RHCl. This RH stands for rhodium. Okay, this is a coordination compound of rhodium called as Wilkinson catalyst. It is used in the hydrogenation of alkenes. Hydrogenation means addition of hydrogen. So alkenes, if we add hydrogen, it forms alkanes, right? So it is used in the hydrogenation of alkenes. So it is a very important catalyst, which is actually a coordination compound, right? Now the chelate therapy is used in medicinal chemistry. For example, EDTA is used in the treatment of lead poisoning. EDTA. It is also a coordination compound, right? Yes, some coordination compounds such as cisplatin. This also in the beginning I have discussed. This is used in the treatment of cancer, right? In the growth of, inhibiting the growth of tumors. Okay, inhibiting the growth of tumors. That means it is used in the treatment of cancer. Now, coordination compounds are of great importance in biological system. For example, the chlorophyll is a coordination compound of magnesium. Hemoglobin is a coordination compound of iron, and vitamin B12 is a coordination compound of cobalt. So this is also a very, very important application. So this is very important to remember. Chlorophyll is a coordination compound of what? It is a coordination compound of magnesium, right? And hemoglobin is a coordination compound of iron. So this is also very important point to remember. Right, these few points. EDTA is used in lead poisoning. Cisplatin is used in the treatment of cancer. Chlorophyll is a coordination compound of magnesium. Hemoglobin is a coordination compound of what? Iron. And the last one is vitamin B12 is a coordination compound of cobalt. So all this you have to remember, and these are the applications of coordination compounds. By this, we come to an end to this chapter. So I hope the concepts that we have covered is clear for you in this whole chapter. So from the beginning, we have discussed various basic terms of coordination compounds. Then we moved on to the major three theories, that is Werner's theory, valence bond theory, and crystal field theory. And we studied each of it in detail as well as the limitations of that. And finally, we moved on to metal carbonyls, the important metal carbonyl bond, which is a very important part, right? The sigma and pi bond formation, as well as the applications of coordination compounds. So I hope the chapter is clear for you. So that's all for today. Thank you.